Hello and welcome to class number 11. This is going to cover the first three sections of chapter 6 in the Smart Book or ebook, and the topic is rate of return analysis. We have studied so far, to kind of recap a little bit, we've studied present worth, annual worth, future worth. What we're going to study next, or today, is rate of return, which basically lets the interest rate be the unknown, and we have to solve for that rate, and we call that the rate of return. Now, I'm going to go back and say first, you should go to the start page in Blackboard, because the schedule keeps changing. As I add more data to the schedule, I think I've got it scheduled up through chapter 7 so far. And you should read pages 154 through 162. That's the sections that we're covering today. This instructor video will be posted in Module 6 because this is Chapter 6. And you're responsible for all of these lecture notes, even if I don't have enough time to cover them all in this video. The last thing is, I always say, if you want to make a good grade in the course, you have to work lots of problems, because this is a problem-solving course. I always say the difficulty is not the answer, it's the problem. It's understanding the problem and being able to convert that to a cash flow diagram. And the only way you get good at that is if you do it a lot. And so that's why I recommend working lots of problems. The first section, section 6.1, talks about the definition and interpretation of rate of return, which we use the symbol I star. So it's a special interest rate. It's an effective interest rate because it has a symbol I, and the star means that it's the rate of return rate. Okay, it's a special rate. Now, the author uses a definition that basically talks about the unpaid balance on a loan, or the interest rate on the unrecovered balance, and so on. I'll let you read that here, but it deals with basically saying that if you lend money or if you borrow money, either way, at some interest rate I, the rate of return is the rate that makes the future unpaid balance zero. Okay, the future unpaid balance is zero. Well, you and I both know that if the future value is zero, how much is the present value? Well, the present value is the future value times 1 plus I to the minus n. And if you multiply anything times zero, you're going to get zero. So it's also true, and that's my definition of rate of return, that the rate of return is the interest rate at which the present value of the cash flow equals zero. So the author in equation 6.2 says if you subtract the present worth of the disbursements from the present worth of the receipts, in other words, this is the positive cash flows, these are the negative cash flows, you're going to get zero if you do it at the rate of return rate. And so if we calculate the present worth of the disbursements and then calculate the present worth of the receipts, subtract disbursements from the present worth of the disbursements from, we'll get zero. And that's basically what I'm saying. I'm just saying, rather than talking about disbursements and receipts, I just say the cash flow, because if it's a disbursement, the cash flow is negative. And if it's a receipt, the cash flow is positive. So I basically say this equation 6.2 could be written as the present worth of the cash flow at the rate of return equals the present worth of the cash flow, and I'm substituting for rate of return, I'm just substituting I star, and that's equal to zero. So that's what when we're solving for I star, we have to solve this equation basically. Now, the author gives you an example, 6.1a, where he sets up basically a loan, a $1,000 loan, and in that loan, he's looking at the unpaid balance as you pay the loan off. He says the bank loaned $1,000 at 10% per year for 4 years. So how much are the annual payments? Well, we know how to convert a present value to a uniform series. Annual payments will be 1,000 times A given P, 10%, because that's the rate, that's the present value. 4 years, that's given, that's $315.47 a year. So the author then, in this case, he says, well, what's the unpaid balance at time zero? The borrower basically owes $1,000 at time zero. And then he says, okay, if he makes a payment, or he or she, at $315.47 at the end of year one, how much will he owe at the end of year one? Well, think about this. If this $1,000 balance is earning interest or being charged interest, either way you want to look at it, at 10%, how much interest do you owe after 1 year? Well, you owe $100, right? 10% of that unpaid balance. So you owe $100 of interest, but you make a $315.47 payment. So how much of that payment is interest and how much just pays off the balance? Well, only the part above the interest is paying off the balance of the loan. That's called principal. And so that's $215.47. So we subtract that from the $1,000 and we get $784.33 is now owed, even though you paid $315 at the end of year one. Right after that payment registers, you still owe $784 because the first $100 of that went to interest. Now, how much interest are you going to owe then at the end of year two if you owed $784 at the end of year one? Well, you're going to owe 10% of $784. So of this $315 payment, $78.45 is going to be interest, 10% of the previous balance, and the rest of it will be principal, or paying off the loan, $237.02. And that will be subtracted from the $784.53 to get $547.51. And this process continues, and when you make that fourth payment of $315, then only $28.68 is interest. The rest of it is principal, and it exactly pays off the loan. So your unpaid balance is zero. And that's basically what he's saying in his definition, that the unpaid balance at time n, whatever that is, will be $0. And if that's the case, then that must be the rate of return. So the table illustrates that the author's definition of rate of return, the unrecovered balance at time zero, in column G of that table is 0. Using my definition, equation 6.2b on the cash flow in column 4, this is the equation. I'm saying the receipts equal to the disbursements. Remember, if you borrowed $1,000, the bank is out $1,000. So that's a negative cash flow from the bank standpoint. Then you're going to pay back $315.47 a year for 4 years. So that means that if we find a present value of that at the I-star rate, that will have to be 0. Well, we already know it's 10%. Because that's how we got the $315.47. So basically, we are trying to find the interest rate that sets the present worth equal to zero. And the author says you can do that by trial and error, which I'm going to show you how to do that, and you can use a spreadsheet function. There's two spreadsheet functions that get you rate of return. One is called the rate function, equal rate in open parentheses, and the other is called the IRR, which stands for internal rate of return. So you'll put equal IRR in open parentheses and then kind of fill in the blanks. So what I'm going to do is take a cash flow and then solve for the rate of return by setting the present worth of that cash flow equal to zero. And so let's look at the cash flow that the author gives you in example 6.2. He says, the HVAC engineer for a company that constructed one of the world's tallest buildings, Burj Khalifa in United Arab Emirates, requests that $500,000 be spent on software and hardware to improve the efficiency of the environmental control systems. Okay, so they're going to spend $500,000 here. That's a negative cash flow. And then he says this is expected to save $10,000 a year for 10 years. Well, that's not very much, right, compared to $500,000. So that's $10,000 a year for 10 years. It's going to be a nice uniform series, and we can draw it across there, 10,000. And then this is the kicker, though. At the end of 10 years, $700,000 is saved on equipment refurbishment costs. So now we get this big cash flow out here also that coincides with the 10,000, but it's 700,000, and that's in savings in equipment refurbishment costs. So we're going to have a to set the present worth of that cash flow equal to zero. So I'm going to say present worth of cash flow at the rate I star equals zero, and I have to solve that equation. Well, what is the present worth of that cash flow? And I'm going to have to guess an interest rate. Well, I'm going to start by just guessing zero because that's easy to calculate. If you use zero as the interest rate, then the present worth is just going to be, the present worth is like minus 500,000, right? That's a present value already. Plus, you got an A series, 10,000, P given A, sum rate I for 10 years, and then you have 700,000 in addition to that. That's a future value, P given F, sum rate for 10 years. So that's your present worth equation. And so when I started with zero, you just add the cash flows then. Okay, because this factor here is going to be 10, and this factor is going to be 1. So this is going to be 100,000, that's going to be 700,000, that's 800,000 minus 500, that's $300,000. Now, I said, okay, let me draw a picture of where I'm at here. This is the present worth as a function of the rate, I, and this is going to be my interest rate. And I'll put a little squiggly here. At 0% interest, I have plus $300,000. And I'm going to try it next at 5%. Well, if I plug in 5% into this present worth equation, and I'm doing trial and error now, I don't know what the rate is that solves this equation. So I used 5, I plug in minus 500,000 plus 10,000 P given A, 5% for 10 years. plus 700,000 P given F 5% for 10 years, and I get $6,946. So it's come way down from 300,000 down all the way down here to $6,946. Well, I'm almost down to zero now, right? I'm looking for where it's going to cross this I-axis. So now I'm going to try 6%. Because I think it's going to cross it. Sure enough, if you go present worth at 6%, you get minus 500,000, 10,000 P given A, 6 and 10, 700,000 P given F, 6 and 10, you get minus 35,519. So at 6%, we're down here to minus 35,519. So somewhere in here is our I star. I star is going to be the value where it crosses this axis. And what we're going to do is just do a ratio and proportion. We basically have two triangles here, this one and this one. And we're going to do the ratio and proportion. So I star is going to be equal to this rate, 5%, plus the difference between these two rates, which is 6% minus 5%, which is just 1%, of course, times this ratio, okay, 6,946, that gets me down to 0, divided by this distance here, from here to here, which would be 6,946 minus a minus 35,519. So if you work that out, you'll get I star equals 5% plus 1% times this ratio. And that ratio turns out to be this 1%, 1.0, 0.16. So this is going to be 1% times 0.16 is 5.16%. So that is, by the way, that's doing a linear approximation, and we know this function is not linear. So when we do this, we're introducing a little bit of error, but it's not a whole lot, and so we will accept that method. So this is the trial and error. You can also use your rate function, and I'm going to show you that with an Excel file. So here we have an Excel file with the year and the cash flow. This particular cash flow had a minus $500,000 at time 0, and then $1,000 a year, $10,000 a year for 10 years, and then an additional in the 10th year, $700,000. So in year 10, it's the 710. And you can solve this using the IRR function. If you do IRR and then you put in the cells from the beginning cell to the ending cell, that's H2, this is column H here, that's H2 through H12, and it will return you that rate of return. Now the author says it'll also return that rate of return if you use the rate function. I use the rate function, which, by the way, this function IRR requires you to have the cells. And it has to be that this one is your year 0 and this one is your year n, okay? And then you have to put any zeros or anything else in there, but in this case it's a nice uniform series. This particular function, the rate function, only works when you know the present worth, you have an annual series, and you know the future worth, okay? So it just uses the values of those things. So when you put in, for example, I'll put it in over here, equal, and then you put rate, and then open the parentheses, it asks you how many periods, how much is the payment, what's the present value, what's the future value. And I put in that there's 10 periods, and I put in the annual equivalent, the uniform series, 10,000. I put in the present value minus 500,000, and I put in the future value, which is plus 700,000. And you can guess a rate here. I guessed 5% because I knew it's close. It actually returned me 5.25%, 5.25, and I'm not sure why it did that. We'd have to look at that again sometime, but either one of these is close enough for the work we're doing. So I'm going to return to the Elmo recording here and go into section 4.2 where the author talks about this, and I pretty much covered this. So I'm going to go now into section 6.3. These are some cautions when using this rate of return method. The first caution is called computational difficulty, and I kind of have in parentheses, not so much when you use it, the app that I presented you with, or Excel, okay? And I think there's one L there. The second caution is that you need a special procedure when you have two or more mutually exclusive alternatives. If you have only one alternative, then you look at the rate of return. If it's greater than the MAR, that's a good project. If it's not greater than the MAR, it's not a good project. So that's how you do it with one. But with two, recall if you had two or more alternatives when you use present worth, annual worth, future worth, any one of those three, you chose the alternative if they were mutually exclusive. In other words, you could only choose at most one. You chose the one with the highest present worth, or annual worth, or future worth. However, in rate of return, you can't do that. Okay, you don't necessarily choose the one with the highest rate of return. You have to look at the difference between the alternatives. And I'm going to give you a very simple example to show you why that doesn't work. First of all, let's assume project A is you invest $10,000 at time 0 and it returns $20,000 at time 1. Pretty good investment, right? What's the rate of return? Well, it's 100% because you got your money back plus you got the same amount back. That's 100% rate of return. So the I star of project A, the rate of return, is 100%. Suppose that project B has a first cost of $100,000, so it's a much bigger project at time 0 and returns $150,000 at time 1. Well, it's returning your $100,000 plus 50% more, okay, plus 50,000 in addition to the 100,000. So that's a rate of return of 50%, which is less than that of A. A had 100%. But you can't just do that and say A is better than B. You have to look at the difference between the higher costing alternative and the lower costing alternative. So in this case, that would be B minus A. So what's the cash flow of B minus A at time 0? Well, B, you have to invest $100,000. A, you have to invest $10,000. So the difference is you invest an additional $90,000 to do B. Well, how much return do you get at time 1 in addition if you do the extra $90,000? Well, you have for B, you get $150,000 at time 1. For A, you get $20,000. So the difference in the return is $130,000. So if you look at the difference, you invested an additional $90,000 and you got $130,000. What's that rate of return on that differential, B minus A? Well, it turns out that that's 44.4%. And our MAR in this case is 20%. So B is better than A in this case, even though its rate of return is lower. So that's the case, an example of the case where your method is different when you use rate of return. The procedure is different for evaluating mutually exclusive alternatives. And we'll get into that a little bit more in the other sections of this chapter. I wanted to illustrate it to you. And so the reason why you choose B over A is that the incremental rate of return, or the rate of return on the incremental cash flow, the difference in cash flows, is greater than the MAR. And that's what you're looking for. The third caution that the author gives you is the cash flows have more than one real positive rate of return. Now, generally speaking, that's not the case. Most cash flows have only one rate of return that solves the equation present worth equals zero. But there are some weird cash flows out there, and those can have multiple rates. It's generally when the sign of the cash flow changes several times. Most of the cash flows we've always looked at in this semester, the cash flow started negative, and then you had a bunch of positive cash flows, and so there was one sign change. It went from negative in year 0 to positive, and then stayed positive, and so there was only one sign change. In that case, there's only one real positive rate of return, if in fact there's any positive rate of return. Okay, at most one. Okay, now the fourth caution is that when you solve for I star and you say this is the rate of return, you're assuming that you can reinvest any revenues that come out of that project at that same rate. Well, the fact of the matter is you may not be able to. Maybe this is an especially good project. For example, Project B we just looked at had a 50% rate of return and your MAR's only 20%. So you're going to have to reinvest the cash flows or this method assumes you'll reinvest them at 50%, okay, which is kind of a stretch assumption. So that's it for today's lecture. I will be working some problems either most likely after the second lecture or class number 12. Thank you.